So this lecture is about another standard signal, that is constant amplitude. We want to determine the Fourier transform of a constant amplitude, that is 1. So for that, we know that Fourier transform of a constant 1 cannot be determined directly because 1 is not a absolutely integrable, that is not absolutely integrable. So we cannot find the Fourier transform directly. Hence, Fourier transform of 1 has to be determined from the inverse Fourier transform relation. As you know, Fourier transform of delta function. As we know, the Fourier transform of delta function is equals to 1. Okay, so using the duality property, as you know, using the duality property, which is given by, if the duality property says, if the Fourier transform of a given signal x of t is given by x of omega, then the Fourier transform of capital X of minus t is given by 2 pi into small x minus omega. This is the property called as duality property. Using the duality property to the given function, where the right hand side is my desired Fourier transform, that is 1. So taking the duality property where right hand side will take it as, so the given function in the right hand side, sorry, here 1, so there is no minus here, correction is, so the Fourier transform of x of t is given by 2 pi into x of minus omega. So desired Fourier transform in the right side we are taking, that is 1. Okay, and in the left side we are going to convert that delta t, we are going to replace t as minus omega, and we are going to multiply 2 pi. So hence, using this duality property, we can write the Fourier transform of right hand side, that is 1, is equal to the left hand side will be multiplied by 2 pi and replace delta as t replaced by minus omega. Okay, so hence the, as we know, the impulse function is always an even function, that is delta minus omega would be always equal to delta omega. So it is equal to delta omega. Hence the Fourier transform of a constant 1 is given by 2 pi into delta omega. Similarly, the Fourier transform of any constant a will be given by multiplied with a, since it is 1, that is given by 1 into this, otherwise it is 2 pi into a delta omega. Okay, so that is the Fourier transform of a given constant is written as this. So this is one way of doing the Fourier transform of a constant. The other way is by writing the Fourier transform of a delta function. So assuming delta function as, from the formula we know that, this is the other method where from the formula we know that x of t is given by minus infinity to plus infinity x of omega e to the power j omega t d omega. This is the formula for inverse Fourier transform. Okay, sorry, I left 1 by 2 pi. So 1 by 2 pi you can add. So this is the formula for inverse Fourier transform. Now considering this x of omega as a delta function, delta omega, and as we know the delta omega function is equal to 1 for omega equal to 0 and 0 for anywhere else wherever omega is not equal to 0. So hence by substituting delta omega in place of x of omega, x of t can be found out, that is Fourier inverse of delta omega can be found out by writing 1 by 2 pi minus infinity to plus infinity del omega e to the power j omega t d omega. Now since delta function is 1 for only one value, that is omega equal to 0, so this integration every limit it is delta function is 0 except at one point, that is omega equal to 0. So hence if you substitute omega 0 in the exponential function, this becomes e to the power 0, which is 1, then the answer to this will be only 1 by 2 pi. Okay, so Fourier inverse of delta omega is 1 by 2 pi. So we can write in this one that Fourier inverse of delta omega is 1 by 2 pi. Hence 2 pi you can take it to the left side, and F inverse you can take it to the right side. It becomes 2 pi delta omega, which is equals to F of 1. So the right side is the desired one, that is the Fourier transform of 1. So hence we can say the Fourier transform of constant 1 is given by 2 pi into del omega. The next Fourier transform for standard signal, which is known as the signum function. So we already know about signal function in the previous unit. So signal function is given by SGN of t. Okay, and we know that signum function is a function where it is represented by this, where for positive values of t it is plus 1, and for negative values of t it is minus 1. So this is the graphical sketch of signum function. Okay, this is the graphical sketch, and the functional representation of signum function is SGN of t is plus 1 for t greater than 0 and minus 1 for t less than 0. Okay, so this function is not absolutely integrable, same as the before one, as it is having value of plus 1 and minus 1. This is also not absolutely integrable. So what we can do is, we cannot do directly, then we can substitute this as a function. So let us consider, instead of signum function, let us consider that signum function is multiplied with the exponential function, that is e to the power minus a mod t, which is multiplied with the signum function, and for which we can consider the limit, and then we can consider the, we can substitute the limit, that is we can substitute the limit, that is a tend to 0. When a tend to 0, the exponential function becomes 1, so hence this is not a problem, so that remains as the signum function. So by doing so, we can write this function as given function. So given is the function x of t, which is given by e to the power minus a mod t signum of t, by limit. So we can add the limit in the beginning, limit a tend to 0, limit a tend to 0. So as per the previous lecture, we know that double-sided exponential function can be represented using unit step function. So that is by doing the limit a tend to 0. Double-sided exponential function can be written as e to the power minus at, that is u of t, e to the power minus at u of t, so that gets multiplied with signum function, so that together they can be written as e to the power minus at u of t minus e to the power plus at u of minus t. Okay, by writing this This can be substituted using the formula of Fourier transform, that is given by x of omega, which is the Fourier transform of x of t, which is given by integration minus infinity to plus infinity x of t e to the power minus j omega t dt. Now in place of x of t, if you are going to substitute this given, that is integration minus infinity to plus infinity bracket limit a tend to 0, the functions are e to the power minus at ut minus e to the power plus at u minus t, and the remaining is as it is e to the power minus j omega t dt. Okay, now we can split these two parts and write it again. So which is given by, and taking the limit to the outside, we'll write limit first a tend to 0, and the remaining we can write it as first one integration minus infinity to plus infinity, and this is e to the power minus at into e to the power minus j omega t into u of t dt. This is one term, and the second term will be integration minus infinity to plus infinity e to the power at e to the power minus j omega t u of minus t dt. Okay, now since there is an impulse function which is u of plus t, so the limits are going to change, that is 0 to infinity, and the value of u of t is plus 1. Similarly here, the value of u of minus t is equal to plus 1 for limit minus infinity to 0. Hence we can write it as this is limit a tend to 0 integration 0 to infinity, and we can add the power of exponentials, then it becomes e to the power minus a plus j omega t dt. Similarly, the second one is minus integration minus infinity to 0, and the value of u of minus t is 1, and we can add the limit, that is e to the power minus a minus j omega t dt. We can close this bracket. Now we can do the integration, but before doing the integration, we can change this limit from minus infinity to 0 and make it as 0 to infinity. But in that case, this exponential sign is going, it is changed from negative to, it is going to change as positive when you change the sign. Okay, now when you change the limits. So by doing so, in the next line, we can write it as this is equals to limit a tend to 0. So the first integration would be integration 0 to infinity e to the power, that is e to the power minus a plus j omega t dt, and the second one will be, will change the limit 0 to infinity. In that case, the e to the exponential sign from the negative, it becomes, so there is earlier it was, okay, earlier it was positive, now it's getting negative, that is e to the power minus a minus j omega t dt. Okay, so by considering that, we will write, that is, it is the first one limit a tend to 0, that is first one e to the power minus a plus j omega by minus a plus j omega, will put as 0 and infinity, and this will put curly braces, and the second one would be e to the power minus a minus j omega t by a minus a minus j omega. This is also 0 and infinity. Okay, now putting the limits, and we'll get it as limit a tend to 0. Okay, the first one would be equal to minus a plus j omega, that is exponential minus infinity minus exponential 0. And the second one also, denominator is minus a minus j omega, numerator e to the power minus infinity e to the power 0. Okay, and also you know that exponential infinity is 0, minus infinity is 0. The remaining is e to the power 0, which is plus 1, and the minus sign is getting cancelled, and the result is going to be the next one, which is equal to limit a tend to 0, which is 1 by a plus j omega minus 1 by a minus j omega. Now if you put limit a tend to 0, it is going to be 1 by j omega plus minus and minus, it becomes plus, or else you can write the minus and do it. We can write the minus first and do it here, minus j omega. Then together if you add it, that is become 2 by j omega. Hence the Fourier transform of a signum function Sgn of t is given by 2 by j omega, or the signum function is Fourier transform pair with 2 by j omega. So we can write this in. Okay, so that's the standard signal known as signum function. The next standard signal is unit step function. As we know from the previous discussion that unit step function is given by the function which is having the value plus 1 for all the value of positive values of t, that is t greater than equal to 0, and it is 0 for t less than 0. That is the unit step function. There is one relationship between unit step function and signum function, that is unit step function can be given by, so also before writing unit step function, we also know that this is the signum function. We can know that we can write the signum function that you defined before, that can be written as it is minus 1 plus 2 times u of t. This is the relation between signum function and unit step function. By taking plus minus 1 to the other side and dividing by 2, you can write u of t is equals to nothing but half of signum function plus half. So this is the relation between unit step function and the signum function. Now if we want to do the Fourier transform of unit step function, you need to do the Fourier transform of the right hand side, that is half of Fourier transform of signum function plus half of the Fourier transform of half is multiplied with 1, so Fourier transform of 1. Okay, so we know already we have done for Fourier transform of signum function and also the Fourier transform for 1. So hence we can write that Fourier transform of unit step function is given by half of, what is the Fourier transform of signum function? That is 2 by j omega. And what is the Fourier transform of half into Fourier transform of 1? That is 2 pi into delta omega. Hence we can cancel the 2 over here and write it. The Fourier transform of unit step function is 1 by j omega plus pi del omega. So that is the Fourier transform of unit step function. We can mark it as this is the Fourier transform of unit step function. Or else we can write in this way also, u of t is Fourier transform pair with 1 by j omega plus pi delta omega. So that's the Fourier transform of standard signal, that is unit step function.